brought to a new location. Then, under the gravity, there's excess power water pressure in the soil. Then is under consolidation soil. And after a long time, all the excess power water pressure dissipate. The soil tend to normal consolidated soil. When we are applying the construction load on the soil, then this load will generate a higher excess power water pressure, and after a long time, then all the excess power water pressure dissipate, and the soil is turned to another state of normal consolidated soil. But if you remove the construction load, now the soil tend to over-consolidated soil. And this soil in the history experience higher consolidation pressure. Then we define it as over-consolidated soil. We know that the behavior of the over-consolidated soil is totally different with the behavior of normal consolidated soil. And when we apply the same load, and the normal consolidated soil will have a larger deformation, but the over-consolidated soil deform not so much. That means properties of soil also depend on the consolidation status. Okay, and that's just now we reviewed the properties of soil and the steady or dynamic soil. Now let's see. We just concentrated the end-dynamic conditions, the deformation and the strength characteristics of the soil, and they are more complex. The first is power water pressure increases with vibration times. We know that during the earthquake, if it's a saturated loose zone, and we will observe that the power water pressure will increase with the shaking. And the second is deformation parameters depends on the strain level. With the strain develop, all the deformation parameters will change with the strain level. And we can observe this phenomenon in the laboratory test. The third is the shear strength and the liquefaction resistance decrease with the vibration times. According to the principle of effective stress, the total stress equal to effective stress plus excess power water pressure. Plus power water pressure. And if the total stress is a constant at this moment, when the power water pressure increase, it will cause the decrease of the effective stress. And the effective stress is also can be used to evaluate the stress status during the earthquake. It will cause or in the vibration, it will cause the increasement of the power water pressure or generate excess power water pressure, and it causes the decrease of the effective stress. Then the decrease of effective stress lead to the decrease of shear strength, even liquefaction occurred. The fourth is residual deformation accumulates with vibration time. And we know that with the vibration, the strain will develop. And in this strain, there's some components of plastic strain. And this plastic strain will not recover. Then that's the residual deformation. And longer vibration and larger residual deformation. Then the relationship between dynamic stress, dynamic strain, dynamic strength, and time is called dynamic constitutive relationship. That means here we can observe that in this constitutive relationship is not similar with steady soil mechanics. In steady soil mechanics, there's only includes the relationship between the strain and stress and strength. But in dynamic constitutive relationship, it not only includes three parts: strain, stress, and strength, but also include time. That means usually in dynamic constitutive relationship, you can find the variable of time. And sometimes if we use plasto-elastic model, then usually we couldn't find the time, the variable of time in the constitutive constitutive model. That means plasto-elastic model can be used not only in steady condition, but also can be used in dynamic condition. Then the basic requirements of establishing the calculation model. We must know how to calculate this. It can be better represent the actual performance of soil, and is simple and practical. When you develop a dynamic constitutive relationship or constitutive model, it can solve the engineering questions. That means your calculation result must similar with the prototype model, or the actual behavior of soil. And this model should be simple and can be used in engineering. If this model is too complex, include many parameters and not easy to get, then we couldn't use it to solve engineering questions. And at present, elasto-plastic model and the nonlinear equivalent visco-elastic model are widely used in seismic engineering. Here I say elasto-plastic model is not only valid in steady condition, but also in dynamic condition. Here, nonlinear equivalent visco-elastic model I already introduced is composed by some elastic elements and viscous elements and plastic elements, and they consist together to create a model, and this model can be described using visco-elastic model parameters. For example, the stiffness and damping ratio. But this is not a real parameter. parameters is equivalent parameters. And if we use these equivalent parameters, and it can easy to explain physically. Then the dynamic response of soil and the dynamic load is related to a series of factors such as the physical and mechanical properties, mass distribution, and the boundary condition of the soil, which is a unique vibration system. And the dynamic response analysis of soil and the dynamic load is an important part of seismic design. And for some important buildings, we must make the dynamic response analysis of the soil structure interaction system. The important part of this is the soil. And the soil dynamic behavior of soil will affect the response of soil. Then it's very important. In the dynamic response analysis, the dynamic performance index of soil, such as dynamic modulus and damping ratios, are used. And we can easily understand the meaning of these parameters and can explain physically. Then, usually, we will use this dynamic modulus and damping ratio to in dynamic analysis of soil. Here, dynamic modulus described the stiffness of soil and the changing of stiffness and the dynamic load. And the damping ratio described the energy loss and the dynamic loss of the soil. Now let's see scattering curves and hysteresis curves. First, the curves with point is the skeleton curves. That's the relationship between the shear stress and the shear strength of the soil when we applying the monotonic load on the soil. Here, this is the skeleton curves. And the hysteresis curves, or we say hysteresis loom. Hysteresis loom composed of unloading branch. You see, this is an unloading branch and reloading branch. Here, this is a reloading branch. Now let's see, from the monotonic, from the initial load, from the initial condition is 0 point. And we applying the load on it, it will deform along the skeleton curves to a certain stress level. Then unloading occurred. Then it will deform following the unloading branch to inverse point and unloading stage end and the reloading stage starts. Then it will deform along the reloading branch here. Perhaps it will go on increase, then reach to a new point and unloading and reloading. Then the hysteresis loom composed of unloading branch and reloading branch is called stress-strain hysteresis curves and the cyclic load. And with the increase of dynamic stress amplitude, the dynamic modulus decreases and the voice of hysteresis loop increase. And what's the meaning of the dynamic modulus decrease? Connect to inverse point. This is a straight line, and the inclination ratio of this line just the dynamic modulus. And we know with the strain develop, we can find the rate of inclination rate of this line will decrease, and this line describes the average dynamic modulus. Then the dynamic modulus will decreases and decreases with the stress increase. Then the width of hysteresis loop. You see, there's a two widths, and we can find two loop, and with different widths. We already know the area inside this loop, the meaning of it. The meaning is that the energy loss and one cyclic load. And the width increase means the energy loss increase. That means with the increase of stress amplitude, the energy loss will also increase. The line connecting the end of several hysteresis loops. For example, if this point represents the ends of hysteresis loops, we connect them together, or we draw fitting curves of them. It's just skeleton curves. And in the beginning, I define it as when we apply the monotonic load on the soil, then it will create skeleton curves, relationships curves of stress and strain. And now I give you the second definition. The line connecting the ends of several hysteretic loops with different dynamic stress amplitudes is called stress-strain skeleton curves of dynamic load. Then, now we already have two methods to create the skeleton curves. The stress-strain curves of skeleton curves is also called backbone curves, is approximately in accordance with the hyperbolic law. Usually the shape is hyperbolic functions curves. Here we can observe it clearly, hyperbolic curves. And in the beginning, from the original point, we draw a tangential line of these hyperbolic curves, or backbone curves, or skeleton curves. Then the rate of this line, G0, is an initial shear modulus. And when we observed is hyperbolic function curves, then this rate in the beginning, G0, is the largest one. Then we can also use Gmax. We can also use Gmax to describe this initial shear modulus. When it deforms to a certain point, and we connect the original point to this point using a straight line, then the rate of this straight line represents the average inclination rate of the energy.